So erosion as the result of wave action. What is a wave? We associate waves with surface water. And waves on the surface of a body of water are generated by the wind. The further the distance the wind can travel over a body of water, the greater the height of a wave. Waves are also generated by earthquakes. We call those type of waves tsunamis. That happens when plates, there's a fault in the ocean bottom, the crust of the ocean made out of basalt, and there's a fault that allows one side of the fault to slip down. That allows a volume of ocean water to move down suddenly. That generates a wave from the bottom of the ocean up and then out in all directions. And as that water approaches the shore, it can be pushed up by the bottom of the ocean into a higher and higher wave. Surface ocean currents are moving due to the wind, and we know what surface ocean currents are based on our understanding of the wind and global winds, and the fact that global winds cause surface ocean currents to move. There is also movement in the ocean, deep in the ocean, due to the convection of cold water from the surface down. So what happens is that, say at the Arctic, you can have water freezing, sea ice. Well, that sea ice freezes, leaving behind the salt that was a part of that liquid water. It stays dissolved in the liquid below the ice that froze. That makes the water denser. It's already cold. Now it's denser, and it sinks down to the bottom of the ocean and then begins to flow along the bottom. But as it sinks, more surface water is drawn towards that area, and so you have ocean currents that are being formed both by the wind and by the convection that starts in the polar regions with cold sinking ocean water. And here we have our surface ocean currents as seen in the Earth Science Reference Table. So you could see here the West Greenland current could easily be caused by that phenomenon I just mentioned. And you see, likewise, these gyres, that's what they call this circular movement of water in the ocean basement, this gyre of ocean currents caused by primarily the global winds and the shape of the ocean basin. So in our neck of the woods, we have a lot of warm water, the Florida current, which moves out and then helps form, along with North Equatorial, into the Gulf Stream, which moves based on global winds across the Atlantic, and that keeps this section of Northern Europe quite temperate, much more temperate than it would be without the ocean current. So ocean currents are very important in relation to climate worldwide. Now, what is a wave anywhere on the ocean? Because there are waves in the middle of the ocean, there are waves at the shore, there are waves on lakes, and waves formed by energy of the wind, or waves are formed by the energy of the wind being transferred by friction to the water. So the wind is passing over the ocean, and there's friction between that matter in the air and the ocean surface, and that friction generates energy that moves in a circular pattern down into the ocean water or the lake water. So here the wind is going over, and then the wind energy by friction is slowed down, and it starts causing water to move in this circular path. And that circular path creates vertically rising and sinking pattern called a wave. The water is not moving in the direction of the wind, but it's moving up and down as energy is drawn into the ocean by the wind. As we had with electromagnetic energy, we then have a crest of a wave. We have the wavelength between two ocean waves, and we have this trough, this area where the energy has sunk down. Here you see the orbital path of individual water molecules at the surface, around and around and around. The frequency of ocean waves or lake waves is the number of wave crests passing a point in a given amount of time, a second. And the period is the time required from the wave crest at point A to reach point B. How often they arrive at A, and then the period, how long it takes them to get from A to B. So that's ocean wave, or a lake wave, or a wave anywhere. Up and down motion. That's why you'll see a duck bob up and down. That's why you see a buoy bob up and down. When you're in a fishing boat just sitting there and the waves are moving you, they're moving you up and down. Just sitting there fishing. Coastal processes in relation to this wave energy cause shoreline erosion. That's the purpose of talking about these waves, beyond the fact that they are inherently interesting in the earth science context. But at this moment, we want to deal with them in relation to erosion. And breaking waves cause erosion. They cause what's called, or the wave energy itself causes the waves to break as they approach the shore. Then they refract, they bounce off. That causes a particular type of erosion. And longshore currents, which is the fact that waves don't approach the shore at a right angle. So if your shoreline is my yellow pen, waves don't come in at a perfectly perpendicular right angle. They come in at an oblique angle. I guess that would be the best way to describe it. And the energy of the wave incoming hits that pen, picks up sand at the shore, and carries it out at the opposite angle. All right, so we come in, we go out, and that erodes the beach, as do the breaking waves, as does wave refraction. We also have here, again, another image of how waves are formed in deeper water with our wavelengths, our crests, our circular motion in the direction of the wind, right? Circular motion. And what happens is, as the ocean begins to shallow, as the depth decreases, the bottom of the ocean begins to give shape to this circular motion of the wave. It makes the waves more elliptical. And that elliptical shape begins to be seen in the way the wave forms above the surface of the ocean. And so what you get is, as the bottom of the sea shallows, you get an elliptical shape, plus remember that the ocean is exerting a force down on the bottom, while at the same time the bottom is exerting a force up. And as more water is being pushed into this shallower and shallower area, there's more force, and the force in response pushes the water up. So thus we get a wave that comes up and crests. And because the water also here is being slowed down, there's friction down here, you get an upward motion, you get a slowing down at the wave base, and you get a building up and a breaking at the top. The breaking because the top of the wave is going faster than the bottom. Here you see a surfer right here going down an 80-foot wave. And again, why would this wave be able to be generated with such height? Because so much volume of water is so quickly entering into a shallow area and gets pushed up very rapidly. The wave crests and begins to break because the top of the wave is going far faster than the bottom of the wave at the bottom of the sea. So you get this giant vertical movement, and then this cresting as the top is racing faster than the bottom. Meanwhile, surfer goes down the side or falls. And you get this curling motion. This elliptical shape is generated by the slow bottom of the wave, right? Creating this elliptical shape at the bottom of the wave, which then is expressed at the top, right? So this motion as the ocean water gets shallower, and here you fall. Then we have coastal wave refraction. What happens there? Well, sometimes you have an uneven distribution of resistant rock along the shoreline, and that resistant rock will create a headland jutting out. So here, a more resistant rock getting hit by wave energy, which generates wave energy that refracts in along the shore, creating some sandy area here. So here the wave energy is less, here the wave energy is very high. And you can see this kind of a landscape in many places where you get this headland jutting out into the sea and then a beach alongside it. Meanwhile, there'll be erosion along the cliff face here, which will take rock along this edge and pound it until it's finally perhaps pounded down into the size of a piece of sand. And here, this area has eroded at a more rapid rate because perhaps the rock is slightly less resistant to, or yes, less resistant. And this last one that we want to deal with in terms of wave generated erosion along a beach is what's called a longshore drift. And I described it before, which is that waves come in at an angle. They come in, they carry a lot of energy, they hit the beach, they pick up sand, they pull the sand out with the undertow, and then that sand is carried down further the beach. And this keeps happening so that slowly the beach is being moved laterally along through space. And we see this easily on Long Island, also on Cape Cod, where here you see Fire Island, where it used to end 1800. Fire Island, where it ended in 1825. There used to be a lighthouse, right? That was the end of Fire Island. But sand has been being moved from Montauk to the east on Long Island all the way to the west over time. And it hadn't taken that long to move a huge amount of sand, which has made Fire Island grow bigger and bigger and bigger. And what's interesting is that at a certain point, once people began to vacation here and have property, it was decided that that really needed to stop. And so they built a inlet, which probably has, with a jetty, which has tried to slow down the creeping, what's called spit formation of this barrier beach. Here are the Rockaways, which are found out in Queens, and you can see they used to end here 1866, and now they've moved 2, 3, 4 miles down until they built a wall, and now the sand has to be diverted around. They have to dredge this to get the sand out and make sure that this inlet remains. But longshore drift, and again, here's the longshore current moving the sand from right to left, moving the sand from right to left. The vocabulary of shoreline erosion includes the word beach. You should know what that means. Sediments eroded from cliffs. Headland with eroded arch. So here's the headland, more resistant, but an area of rock that was less resistant. A cave. And then sometimes you can have a stack or a stump of ocean rock that had, again, resisted erosion and is above sea level, the mean high tide, and is exposed at low tide. So that's our shoreline erosion. There's not much more to it than that. One thing, of course, that people do worry about is that their beach might be eroded away. Imagine you buy a piece of beach property and the sand is slowly being taken away by the sea because of longshore currents. And so what you see here is a solution. People have put in what are called groins. And the longshore drift, if you look carefully, is from right to left. How do you know that? By looking at this picture. Well, on the right side of every groin here, you can see the sand has built up, as opposed to the left side. The sand juts out further here than on the left side. The sand juts out much further here than on the left side. That's because the sand is being carried in this direction and builds up along the groin. And that's the purpose of this structure. You see this with jetties, sometimes riprap, which is along the shore, lateral, bulkheads, which are larger things. You can see those all around New York City. And they all have pluses and minuses in terms of maintaining the integrity of your beach. I'm going to stop there because Chica wants more attention.